Hello, hello. Good afternoon, everybody. Welcome to my tutor. Let us continue the discussion on higher order ordinary differential equations. Okay, in the last lecture, we shall discuss that in this lecture, we are going to discuss the right hand side is polynomial functions. R of x is equal to x raised to n. Okay, so for this session, the important part is uh, I need a few formula from you people. The first one is 1 plus x raised to minus 1 is equal to 1 minus x plus x square minus x cube and so on. You know that this is the Maclaurin series of 1 upon 1 plus x when the absolute value of x is strictly less than 1. The next is in place of x I am writing minus x, 1 minus x raised to minus 1. So this will be 1 plus x square plus x cube. The next one is 1 plus x raised to minus 2, which is 1 minus 2x plus 3x square minus 4x cube, and likewise 1 minus x raised to minus 2, which is 1 plus 2x plus 3x square plus 4x cube and so on. Okay, so let us start the session with the example. We have given the differential equation d2y by dx square plus 16y is equal to x raised to 4. Yes, throughout this lecture, we shall not much concentrate on the complementary solution. We shall concentrate only on the particular integral, because in today's session I want more discussion on particular integral. So let us start with this example. d2y by dx square plus 16y is equal to x raised to 4. The differential equation is d square y plus 16y is equal to x raised to 4. Excuse me, just a minute. So actually there is some connection error I am getting. Okay, so let us continue the example. d2y by dx square plus 16y is equal to x raised to 4. So we have an auxiliary equation, d square plus 16 is equal to 0. So which has two factors, 4i and minus 4i, which can be represented by 0 plus or minus 4i. We know that 0 is the real part and 4 is the imaginary part. So how do we write the complementary solution ycx? Real part becomes the power of exponential, which is e raised to 0x. Then we have cos, this imaginary part 4 is here, cos 4x plus sine 4x, and then we multiply by the constants c1 and c2. So we have the complementary solution is c1 cos 4x plus c2 sine 4x, where c1 and c2 are the constant quantities. Okay, now let us go for the particular integral. Actually I am very much interested in this polynomial case. So let us assume that the particular solution is x raised to 4 plus bx cube plus cx square plus dx plus e. This is the solution of this differential equation y double dash plus 16y is equal to x raised to 4. I shall come here that why we are assuming x raised to 4 plus bx cube plus cx square plus dx plus e. Okay, so suppose, see, in last two lectures, if right hand side was the exponential, then our assumption was this: if the right hand side is either cos or sine, then our assumption was this. So what is happening here? The derivative of exponential is exponential, right? The derivative of cos is minus sine, and derivative of sine is cos. So actually what we are doing, we are combining all possible derivatives. So exponential is only the derivative itself, exponential. The trigonometric functions cos or sine has the derivatives cos. So here we are combining, make the linear combination of sine and cos. So here the right hand side is x raised to 4. So the derivative of x raised to 4 is x cube. The derivative of x cube contains x square. Derivative of x square contains x, and derivative of x is the constant. So all derivatives of x raised to 4 we have, right, and we make the linear combination. So the assumption becomes x raised to 4 plus bx cube plus cx square plus dx plus e. Then the first derivative is this. I am not going to discuss the first derivative. This is the second derivative. Now we are assuming that this is the solution of this differential equation. So let us substitute the value of y double dash and y to this equation. So what we have, yp dash double dash is 12x square plus 6bx plus 2c plus 16 into y. Y is this x raised to 4 plus bx cube plus cx square plus dx plus e is equal to x raised to 4. So what we have, now let us try to compare the coefficients. So here the coefficient of x raised to 4 is 16x, so the term is 16x raised to 4. This is the term 4x cube, 16bx cube. Now for x square we have 12a and here c, so 12a plus 16c it is. Now for x, what we have, 6b plus 16 into d and plus constant 2c plus e equal to x raised to 4, right? So now how I am representing x raised to 4, x raised to 4 plus 0x cube plus 0x square plus 0x plus 0. Okay, so what we have, 16a is equal to 1 because 1 is the coefficient of x raised to 4, right? So the first equation is this. Second equation, 16b equal to 0 after comparing the coefficient of x cube. The third equation, the coefficient of x square, 12a plus 16c, and here it is 0. The coefficient of x, 6b plus 16d is 0, and the constant coefficient 2c plus 16e equal to 0. Yes, so how many equations we have? Total 5 equations and 5 variables. From this we have a, from this equation we have b. This is not a tough calculation. You can substitute value of a here and we get c. We can substitute the value of b and we have d, which is 0. We substitute the value of c here, which gives us e, which is 3 upon 32. So let us substitute all these values to this assumption. So we have ypx is this, x raised to 4 minus 3 upon 4x square plus 3 upon 32. And therefore the general solution, we know that the format of general solution is ycx plus ypx, so which is c1 cos 4x plus c2 sin 4x plus x raised to 4 minus 3 upon 4x square plus 3 upon 32, where c1 and c2 are real numbers. Okay, so now let us discuss uh, how do you find ypx by another method. These shortcut methods we have already seen in the case 1 and case 2. Now for the polynomial case also we are going to discuss the same thing. So we have ypx is this 1 upon fd into rx. What is f of d? It is d square plus 16. And what is rx? Rx is x raised to 4. Yes, okay, so now what we do? We find the minimum degree term. So this term has degree 2 and this term has degree 0, 16 into d raised to 0. So the minimum degree term is this 16. We take minimum degree term common, right? So let us take 16 common. So now what we have, when do we take 16 common, we will have d square upon 16 and 16 upon 16 is 1 multiplied by x raised to 4. So after by taking 16 common, we have this quantity 1 upon 16 into 1 plus d square upon 16 into x raised to 4. Okay, so now what is this? This is 1 plus d square upon 16 raised to minus 1 into x raised to 4. Now look at this term, 1 plus d square upon 16 raised to minus 1. If I consider this as x, then this is 1 plus x inverse, and we know that 1 plus x inverse is what? 1 minus x plus x square minus x cube and so on. In place of x, we assume d square upon 16. So what we have? 1 upon 16. So look at here, 1 minus x, x is d square upon 16 plus x square. So it is plus d square upon 16 whole square and continue this manner into x raised to 4. What do we mean by the derivative? D square. D is derivative. So this represents the second derivative of x raised to 4. This is d square whole square is d raised to 4. So fourth derivative of x raised to 4. If I look at the next term, then it is d square cube, which is the sixth derivative. We know that the sixth derivative of x raised to 4 is 0. So we omit the next derivative terms. So this is 1 into x raised to 4 is x raised to 4. The second derivative of x raised to 4 is 4 into 3, which is 12 x square upon 16 we have. This is the fourth derivative, which is 4 factorial is actually 24 divided by 16 square, right? Okay, so let us simplify this. This is not the tough task. Minus 3 upon 4x square plus 3 upon 32. This is ypx. This is same as we have evaluated. Okay, so now let us go for the next example. The next example is find the particular integral for y double dash plus 2y dash plus 3y is equal to 2x square. So we have the particular integral as this 1 upon f of d into rx. What is f of d? Look at here, d square plus 2d plus 3 and rx is 2x square. Okay, now what we did in the last example, we just observed or we found the minimum power of d, which is here 3. We take 3 common, so we have 1 plus d square plus 2d upon 3. This is very much a simple calculation now. This is d square plus 2d upon 3 all raised to minus 1, right? So this is 1 plus x inverse. I am considering this as x, right? So we have by the formula 1 minus x plus x square and so on into x square. Okay, so this is 2 upon 3. 1 into x square is x square. Right. Okay. So first let me expand this thing. 1 minus this is d square upon 3. This is now minus 2d upon 3. Okay. Now look at here, d square plus 2d whole square. Concentrate here on this term. So this is actually a plus b whole square, which is a square, that is d raised to 4 plus twice ab, which gives us 2 times 2d into d square, which is 4d cube, plus 2d square is 4d square. So this represents the fourth derivative of x square. You know that that is 0. The third derivative of x square is also 0. The second derivative of x square is constant. So I am concentrating only this thing. So this is plus 4d square divided by 3 square is 9 into x square. See, if I consider the next term, then it is raised to 3, right? So at least d cube term we have. The derivative of x square, right? So third derivative of x square is 0. So all other derivatives of x square are 0. So we omitting the other terms. So this is 1 into x square. The second derivative, which is 2 divided by 3. The first derivative, which is 2x. So it gives us minus 4 upon 3x. And this is the second derivative, which is constant 2. So it is 8 upon 9. By the simple calculation, we have the particular integral 2 upon 3x square minus 8 upon 9 into x plus 4 upon 27. Okay, what next? Yes, this is a very important example. Third derivative of y minus y is equal to x cube. Okay, so let us solve this differential equation. So in the solution, we go for complementary solution as well as particular integral. This is d cube minus 1. So this is d cube minus d, right? Actually, this is y triple dash minus y dash. I made a mistake here, right? So when I take d common, then it is d square minus 1. So this is d minus 1, d plus 1 equal to 0. Please make sure about the exercise. This is y dash, not y. Otherwise, this is not true. So it has three roots: 0, 1, and minus 1. So now how do we write the complementary solution? E raised to 0x, e raised to minus 1x, and e raised to 1 into x. We multiply by the c1, c2, and c3. So this is nothing but c1 plus c2 into e raised to minus x plus c3 e raised to x, where the constants are real. Okay, so this is the complementary solution, but I represent by this. I want little bit discussion on this, that's why I'm writing. Otherwise, this is not the important step. So I'm representing this c1 as c1 into 1, the function with red color. Likewise, this e raised to x. Now go for the particular integral. So the particular integral is this 1 upon d cube minus d into x cube. The minimum degree is this term, right? This term has the minimum degree 1. In last two examples, the minimum degree term was constant, but here it is not constant term, it is d. So let us take d common. So we have d square minus 1 into d x cube. I represent this as I am taking minus sign common because otherwise I want to apply the formula of 1 upon 1 minus x square. So this is minus 1 upon d into 1 plus d square plus d raised to 4 and to multiply by x cube. Yes, so here what is happening? See, in last two examples we had only the bracket term and we apply all these derivatives to the polynomial, but here we have two terms. One is minus 1 upon d and another one is 1 plus d square plus d raised to 4. So now the question arises, which term I have to apply first, minus 1 upon d or 1 plus d square plus d raised to 4. I am choosing this term 1 plus d square plus d raised to 4. Yes, I shall explain you that why I am choosing this term and what will happen if I apply first minus 1 upon d. So let us apply first 1 plus d square plus d raised to 4. So minus 1 upon d as it is. 1 into x cube is x cube. The second derivative of x cube is 6x. Fourth derivative is 0, so all other derivatives are 0. Yes, d is derivative. So what is 1 upon d? That is d inverse. Inverse of derivative is integration, that we know. So let us integrate this quantity. The integration of x cube is x raised to 4 upon 4 with this minus sign. The integration of 6x is 3x square with this minus sign. So our ypx is this minus x raised to 4 upon 4 minus 3x square, and therefore the general solution of this equation is ycx plus ypx. Ycx is this and ypx is this, with c1, c2 and c3 are real numbers. Okay, so this is the shortcut method. Now let us apply the assumption. Suppose ypx is x cubed plus bx square plus cx plus d. Now I am writing ypx as this. See, x cube I am representing with blue colors. X square x and d is nothing but d into 1. Okay. Now in the last two lectures we discussed that we must compare our assumption with ycx. So let us compare with ycx. Ycx is this c1 into 1 plus c2 e raised to minus x plus c3 e raised to x. Right. See, sometimes what happen if you remind the exponential case and trigonometric case, then sometimes denominator was 0. Why that situation we had? That is only because of the assumption uh, is already contained in ycx. So see, x cube is different from these three functions, 1 e raised to minus x and e raised to x. Likewise, x square and x are also different, but this one is here. So this is the repeated term. That means this assumption doesn't work here, right? So what we do to avoid this situation, we multiply by x. So we have x into x cube plus bx square plus cx plus d. That time also we did the same thing. We multiply exponential function or trigonometric function by x when the denominator were coming 0. See, so this is a into x raised to 4 plus bx cube plus cx square plus dx. And you just find the derivatives and substitute to the equation and find the constants, right? So ax raised to 4, so the constant value is of a is minus 1 upon 4 plus bx cube. There is no cubic term here. What does it mean? B is equal to 0. This is cx square, so c is equal to minus 3, and dx, there is no dx, so d is equal to 0. Answer already you have, right? Okay, so let us go ahead. Ypx, as I discussed, x raised to 4 plus bx cube plus cx square plus dx. Yes, now let us apply this bracket first. See, this is the solution when we applied the rectangle first. Now we applied minus 1 upon d first. So this which represents that we have to integrate this quantity. So the integration is x raised to 4 upon 4. Then into 1, second derivative of x raised to 4 upon 4, and fourth derivative of x raised to 4 upon 4 gives us this. So this is the solution when we applied this first, and this is the solution when we applied this first. So the difference is here, the constant. But our usual method says that there is no constant term, because this constant term, see, if I consider c1 equal to minus 6, then this constant term appears here, which is not possible, because particular integral must be linearly independent with this, right? So when do I apply minus 1 upon d first, it gives me some constant quantity which is not true, right? So if possible, in other examples also, we always apply integral quantity at the end of the example. I mean, first we apply the derivative quantity and then we apply the integral quantity. That is only because otherwise there are chances that the some terms may be conflict with the complementary solution. Okay friends, so now let us go for the analysis. This was the method, undetermined coefficient methods. If the right hand side is c into e raised to x, then our assumption was ypx equal to k into e raised to x. If the right hand side is sine or cos, then our assumption is ypx equal to alpha sine x plus beta cos x. If the right hand side is polynomial, then our assumption is this. We keep in mind that how do we design the assumption. All possible derivatives we have the linear combination of all possible derivatives. And finally, when do we assume this thing, we never forget to compare each term with ycx, right? So that's why I mentioned here separately, don't forget to compare with ycx. Yes, in the next lecture, what will be Rx? That you know very well. All three primary cases we have discussed: exponential, trigonometric, and polynomial. Now we are going to combine exponential into polynomial, exponential into trigonometric, and trigonometric into polynomial. Don't forget to subscribe. Thank you, everybody. Let us stop here.